Hi class, let's do flow and the equation of continuity. Okie dokie, so flow. Flow is talking about fluids here. So we got rivers and fluids and pipes and fluids that are going past airplane wings and so forth in this chapter. So flow is the volume of fluid passing some imaginary gate. You know, you've got some kind of space surface, and then the liquid or gas is flowing through that imaginary plane. So uh, that's something to keep in mind. So you got some kind of clock, gatekeeper. Okay, and then it's going to happen in some period of time. So that's a per unit time. And so the symbol we're going to give to flow is Q, and that's going to be capital V for volume over time. Ta-da! So then for pipes in particular, when you can relate the cross-sectional area of the pipe and the fluid velocity inside that pipe. And I'm not going to derive it, but suppose you had a pipe, then inside a pipe of cross-sectional area A, cross-sectional, no, cross-sectional area, the average fluid velocity, and we're just going to pretend usually that the average is just the velocity. So the fluid moves with velocity little v. So we got a little v already, we got a big V, little v. Different things, that's volume up there. It's volume. And this is velocity down here. But the Q is the same, and it's going to be area times velocity. And you can kind of check the units. So if you have cubic meters for volume and seconds for time, you got meters cubed over time there. And area is square meters. Then you times that by meters per second. So you got the meters squared times meters, and that is indeed meters cubed divided by seconds. So we're all right for units. And then the idea is if you start with a big pipe, and then that pipe gets narrower, then the cross-sectional area, so this first area here would be A1, and it's going to have some velocity 1. Well, you got the water flowing through there, and it's going to go through a narrower bit of pipe, so A2 with some velocity V2. And you can imagine if you're cramming the same amount of flow through the wide pipe, it's going to have to travel quicker if it gets through there, because Q1 is equal to Q2. So the fluid has to get through there somehow. So you can substitute that little guy in there and to come up with area 1 times velocity 1 is area 2 times velocity 2. So substitute that down there. This is called things. This is called the equation of continuity mostly. Equation of continuity. Fancy language there. It's a statement of conservation of matter. Especially if you got an incompressible fluid. This is just saying that no fluid disappears from the system. As it flows through the pipe, Whatever comes through pipe 1 has to go through pipe number 2. So this is conservation. My handwriting's gone to pot. Conservation of matter. But the book calls it equation of continuity. That's good. And then other subtlety here, not subtlety, but if you had, if this broke up into branches after that, so if that pipe split off into more pipes like that, we've got 3 pipes over here. What you do there is you put an N in front. So this is the number of pipes for the first half of the problem, and then this is the number of pipes for the second half of the problem. So you can split up the pipes into more pipes if you want to, and keep track of the accounting with, you start with 1 pipe and it splits into 3, so you put 1 there and you put 3 there. All right, let's do an example of number 5 in the book, which is the Hookah Falls example. So here's number 5 in the book. It's noting that the falls are quite lovely, and for this particular river, the average rate of flow is 300,000 liters per second. And so it's going to ask us some questions, but let's convert this right away. So let's change this into meters units. Let's just multiply right there. So so how do we get liters into actual, what is the unit anyway for rate of flow? This liters should be cubic meters. So if you recall, maybe you never knew this, maybe it's old hat, but 1 liter is defined as a cube of 10 centimeters on a side. So that's 1/10 of a meter, and you got to cube it. So there we have our units canceling. 0.1 cubed is 1 over 1,000. So we just drop a factor of 1,000 from this, and we get, ooh, that's interesting. Get that back in there. We get cubic meters per second for our rate of flow Q. All right, then it says, what does this all say? So gives us that the river gorge at the side of the falls narrows down to a width of 20 meters and a height of 20 meters. So let's just go ahead right away and say, well, you got width times height, and that's going to be a cross-sectional area. So width times height, and that's 20 times 20, or 400 square meters. So that's our gate. The water all has to go through that gorge, so it's going to go through this gate of that area. Imaginary. Okay, then it asks questions. Question A, what's the average speed? And for that, we need our flow formula. So flow is equal to area times velocity, which we can divide the A to both sides to get velocity is Q over A. We know those numbers. That's 300 cubic meters per second, and then the area is 400 square meters. And those 2 instances of meters cancel with 2 of those, so we're good here. 3 divided by 4 is 3/4, and then that's in meters per second. That wasn't so hard. So then type problem B. What if you go downstream? So there's the waterfall, and then it goes back into the normal sized riverbed, and it says that the width there is 60 meters, and the depth is about 40 meters. So for that, the area is width times height. So let's see, 65 meters to 24 with a couple of zeros, 2,400 square meters. And it wants to know the velocity. What's the velocity in this new configuration? Same formula, rate of flow divided by area. So that's going to be 300 cubic meters per second divided by 2,400 square meters. So that's more like 3/4 there. So it's going to be 3 over. Divide that by both sides. It's like 8. It's an eighth. It's an eighth. So 0.125 meters per second. So it's slower. Oh my goodness. So physics works again. And once you get downstream and the river widens out, by gum, the velocity of the water moving through that riverbed is lower.